Hello and welcome back. In this video we will start looking at section 1.4, which is on complex numbers or imaginary numbers. So to begin with, for some motivation, there is no real number x such that x squared is going to be equal to -1. And this is something we've looked at before, but just to reiterate, if we tried to plug in a positive number for x in here, well, a positive number times a positive number is positive, so x squared would also be positive. So it can't be equal to -1. If we plugged in 0, well, 0 times 0 is 0, so that doesn't make this true either. And if x is negative, well, a negative number times a negative number becomes a positive number, and it can't be equal to -1 either. So there is no real number that I can plug into here, plug into x, to make x squared equal to -1. However, it would be useful if there was such a number. So let's invent one. And this is essentially the thought process here. We will call the imaginary unit I the number that is the square root of -1. As in, if you were to square I, we get -1. Now, we know that I can't be any real number. It can't be something like 2 or 6/2 or -13/6. It can't be a positive number, a negative number. It can't be 0. It's not a number that in the traditional sense of a number. This is something that we have purely made up to satisfy this equation right here. However, what we want is in fact a number. And with numbers, we should be able to add them, multiply them, do whatever we want. So what we'll do is we'll just treat I like a number, just not any of the numbers that we're familiar with. So let's do some examples here. So the square root of 25, of -25. Remember that I can pull this apart into the square root of -1 times the square root of 25. We can always pull the square roots apart like this. And here, the square root of the square root of -1, I spoiled it, is I. And the square root of of 25 is 5. And so we get I times 5. Usually, we put the number in front of the I. So this will be 5I. And this is all there really is to it. If we want to take the square root of a negative number, an I pops out. So we kind of think of this as the square root of -25. Well, it's just going to be I times the square root of 25, which is 5. When we write complex numbers are any combination of real numbers and I, and this is going to be standard form. And the standard form, we will put the part out in front that is completely real, as in there is no I in the part that's out in front, and we'll put all of the I's in the back. So we'll have A plus BI. A and B are going to be real numbers. So for example, I have some written down here. We could say have -4 plus 6I. So A here would be -4, and 6 would be B. We call A the real part, and B is going to be the imaginary part. For the obvious reason, B has an I attached to it, and I we've called the imaginary number, or the imaginary unit. If a number doesn't have this A out front, and it's only an imaginary part, we'll just call this a pure imaginary number. It doesn't have a real part. So again, here are some examples. And we can see, okay, so here's the real part. And here's the imaginary part. For a number that looks like this, that's just 2 times I, it doesn't really look like a complex number in standard form yet. We'll have to write it in standard form. So we have the 2I part at the back, but at the front, we can just write 0 plus 2I. Now this looks like standard form. We have a real part, and an imaginary part. Again, if we have just a pure real number, so 7 is just a real number, it's one that we're familiar with, but I can write this as a complex number, say writing 7 plus 0 times I. Anything times 0 we can just get rid of, so when I write this, I could cancel out the 0I and just write a 7. But if we want to write this in standard form, so that we have a real part and an imaginary part, I will need to include the 0 times I there. Okay, so when are two complex numbers going to be equal? Well, when the real parts are equal and when the imaginary parts are equal. So this is essentially what you would expect. Numbers are equal when all the parts of the numbers are equal. And this is just something that is necessary to mention, but should be obvious when it comes up. And one thing I want to note here is there is a distinct similarity between a plus b times I and a plus b times x. I, again, kind of looks like a letter. It could be a variable. In this case, it's not. It has a very specific meaning, but it kind of looks like it. And that similarity we're going to exploit. Essentially, when we want to add or multiply, subtract, divide, do anything with a complex number, it's often easier to treat it like a polynomial, because we've been working with polynomials for a while, and add it like that. So let's look at some examples. Let's add and subtract some complex numbers. So we'll first do this very abstractly. We have a plus bi plus c plus di. If we treat these as polynomials, we have some like terms that have an I in them, and we have some like terms that don't have an I in them. So let's put these next to one another. We've got a and c are the like terms without an I, and the b and the d are going to be the like terms with an I. And now what I'll do is, in order to write this in standard form, I have to have a real part and an imaginary part. So the real part, a plus c, I'm going to put this out in front. The imaginary part, I'm going to factor out the I, and I'll have a b plus d left over. So again, real part, imaginary part. Fairly straightforward. Again, everything should work roughly how you would expect it to. We just factor out the I and rearrange the terms. When we're subtracting, same thing happens. I have, when I distribute this negative sign, let me do that first before I do anything else. So I have a plus bi, and I need to distribute this negative sign across the parentheses, minus c minus di. And now I will arrange this with like terms. A minus c will have the two terms without an I out front. Next, the two terms with an I. And then after that, now I can write this in standard form. So the a minus c, this is going to be the real part because it doesn't have an I in it. In the back, I can pull out an I, and I'll have a b and a minus d. And this will be the imaginary part. So we can add and subtract imaginary numbers. We have this formula, but everything is essentially exactly what you would expect. So let's do some examples with real numbers. And I'll do this in a way that will make this a bit quicker. We have 5 minus 2i plus 3 plus 3i. What we'll do is we'll take the real parts and we'll add them together. And then we'll take the imaginary parts and we will add them together. Note that we have a negative 2 and a plus 3. And each of those is being multiplied by I. And then I can simplify. 5 plus 3 is 8. Negative 2 and 3 is plus 1. So I could write this as 1i, but anything times 1 is just itself. So I can simplify that to be a little bit nicer. So 8 plus I, again, real part, imaginary part. The last example, we'll just subtract. And again, to do this fairly quickly, we have the two real parts, and let's subtract them. So I'll take 2 minus 12. And then I'll have the imaginary parts. I have a 6. And here I have minus I. So we can think of this as minus 1i. And I've got to subtract it. So I'm subtracting a negative sign. Subtracting negative 1. Okay. There's a couple of negative signs floating around. But again, I'm going to be subtracting negative I. So I'm going to be subtracting negative 1 there. 2 minus 12 is negative 10. And here, 6 minus a negative 1. The two negative signs cancel out. And 6 plus 1 is 7. And we have just added complex numbers. Or sorry, subtracted complex numbers.